In the last lecture, we showed that if you add a layer to represent the stratosphere, we can explain why the increase in carbon dioxide in the atmosphere causes a warming of the troposphere, but a cooling of the stratosphere. And this was achieved by the energy balance at the surface, at the troposphere and the stratosphere. And by solving this equation for the temperature of the stratosphere, we were able to show that if there is no absorption of solar radiation, then the stratosphere will behave like troposphere, and as the carbon dioxide increases, the emissivity of the stratosphere increases and the stratosphere warms. Okay. But if you include the absorption of solar radiation by ozone and assume that emissivity of the stratosphere is quite small, which is well known because it is a very thin layer, one can show that increase in emissivity of the stratosphere due to increase in CO2 will cause a decrease in temperature. So, this is one way to understand purely based on energy balance, but you can also explain this by the way temperature changes in the troposphere and stratosphere. In the troposphere, temperature decreases with height, because most of the radiation is absorbed at the surface, and then the atmosphere gets energy from the earth's surface through radiation, evaporation and turbulent heat fluxes. So, that is why in the troposphere temperature decreases with height. In the stratosphere, the major warming occurs directly by the absorption of solar radiation by the ozone layer that is there. Okay. And so, the temperature in the stratosphere increases as you go up. Okay. Just based on the difference in the way temperature varies, you can qualitatively explain why increase in CO2 causes warming of the troposphere and cooling the stratosphere. Okay. Now, we want to extend these ideas to many layers of the atmosphere. We were able to explain most of the results for the earth by using a 1 and 2 layer model. Okay. But if you go to other planets which have much thicker atmosphere, then you will not be able to get the result you get for earth. Earth is simpler to model because the atmosphere is not very thick. The surface pressure is about 1 atmosphere. We go to Venus, which we will discuss later in this course. Venus surface pressure is about 100 times that of earth. So, it is not possible to treat Venus with a 1 layer or 2 layer, we need many layers. Okay. So, to illustrate that, I have here shown you a atmosphere with n layers. Okay. N can be any number. But to make our analysis simple for the purpose of classroom discussion, I am going to assume that all the layers are completely transparent to solar radiation, so that the solar radiation after reflection goes all the way through and is absorbed at the surface. Okay. On the other hand, these layers we will assume are totally opaque to earth's radiation, completely absorbing. That means like a black body. So, you can see that there are no emissivities mentioned here, because each layer acts like a black body. Okay. So, each layer absorbs radiation emitted from the lower layer and emits equally in both directions. Okay. So, remember this simple model in order to make our analysis manageable, but you can based on this construct more complex models. Now, let us look at the energy balance. right at the top of the atmosphere, the absorbed solar radiation is incoming minus reflected, right, that is absorbed solar, that has to be equal to the radiation emitted by the topmost layer. Remember, because all layers are black, totally opaque, no radiation emitted by the earth's surface passes through the atmosphere and goes out. The top layer is totally opaque, so only that layer can emit radiation, that is sigma T1 to the power of 4. Okay. Now, if you go to the next layer, the top layer, it absorbs radiation emitted by the lower layer T2, but it emits in both directions, because the surface is can emit in both directions. So, this is the equation for the top layer energy balance. This is the flux balance at the top of the atmosphere. So, when you balance the energy absorbed by the first layer this much and energy emitted in both directions, you get the following result for sigma T2, because we know sigma T1 from here. So, substitute that here, you get this result. So, you notice that layer 2 just below layer 1 has double the value of this layer. Okay. Now, this should already give you a hint that if you do the next layer, which absorbs radiation from layer 3 and layer 1 and emits in both directions, this will be 3 times this value. So, this is now logic can be extended to n layers. So, the nth layer will have radiation emitted by that layer as equal to n times this quantity. So, the bottommost surface, the energy balance is it emits this much, it absorbs the lowermost layer of the atmosphere which emits downwards, and the radiation from the sun which go through the transparent atmosphere to the surface. So, if you add this also, you will get the following result, that the sigma Ts to the power of 4 is n plus 1 times radiation absorbed by the whole system. Okay. Now, this is a very interesting result which shows for the same amount of radiation absorbed by the whole system from the sun, the temperature surface is n plus 1 times larger. Okay. So, this shows how as the number of opaque layer goes on increasing, the temperature surface will go on increasing, because more and more radiation is trapped. Okay. And this is what happens in Venus. Venus has a much higher temperature than Earth, and it is because its atmosphere is very thick, and so you are represented by many layers, typically around 70 layers. Okay. And you will get the answer. This I will discuss later when I talk about Venus, but you must remember that to get the temperature of the Venus surface as measured by an instrument sent by parachute into the Venus atmosphere, one has to assume a value of n around 70. Now, you might ask me, how did you get the value 70? You cannot explain that from this model. Okay. This model will not tell you what is the appropriate number of layers to be used in a given situation. Okay. So, we will have to come up with a much more sophisticated analysis to understand why Venus is so hot, but this simple analysis gives you the hint that since Venus is a very thick atmosphere, there are many layers whose emissivity is close to 1. And so, we will come to that issue when we discuss the Venus greenhouse effect, which is one of the most powerful greenhouse effect that we know of. Now, why is this so interesting is because according to astronomers, when our solar system was formed and our planets first were born, Venus and Earth had very similar dimensions, diameter and so on, and similar composition. Okay. That is 4.5 billion years ago. Now, in this long period, Earth's atmosphere evolved in one direction. Both Venus and Earth had lots of carbon dioxide in the beginning, and Earth slowly lost its carbon dioxide and we got more oxygen, and carbon dioxide, which was maybe around 70–80%, now is around 400 parts per million. Well, Venus did not lose its carbon dioxide. Okay? Actually, it gained some carbon dioxide from the surface. So, because of that, Venus became very hot. Now, this is important to understand, because Venus and Earth started around the same time with the same composition, and Venus went one way to become a very hot planet which is not livable, while the Earth evolved to be a beautiful blue planet with the right temperature for many living beings to exist. We need to understand why, because that is very important, because the fact that Venus and Earth had the same beginning and Venus became a hothouse, while Earth became very livable for many living beings, should be understood, because one cannot rule out that the way we are burning fossil fuels on Earth, if we started burning all the fossil fuels that you can extract from deep inside the Earth, one cannot rule out the fact that Earth will become like Venus. Okay? So, that is why it is very important to understand how Venus became so hot and Earth remained at a very reasonable temperature. But to do that, we have to do a more sophisticated model than this model. This model is all right, tells you that we cannot model Venus with 1 or 2 layers, that you can easily check, and I will come to that when I discuss Venus. So, we use n equal to 1 like we did for Earth, we will not get the correct answer for the albedo of the Venus and the amount of radiation absorbed from the sun by Venus. Okay. So, we will have to come up with a more sophisticated model, which we will do a little later in the course. Now, before I move on to other topics, I want to extend this analysis of the 0 dimension model we have been doing so far to 1 dimension, in which I want to take into account variation with latitude. Now, why is this important? This is important because you know that the polar regions of the Earth are covered with ice. Okay? And over the long history of the Earth, the amount of ice in Earth has varied a lot. Okay? Sometimes the ice covered the entire Earth, the so called snowball Earth, which we will talk about later, and there were times when the ice completely melted and Earth became completely ice free. Okay. So, it is good to be able to model the latitudinal variation of temperature of the Earth and find out where is the ice line, where is the ice stop, as it stops some polar region, at what point the ice line stops and ice free latitudes begin. It is important to know that. Okay. To do that, we need to understand the variation of temperature of the Earth with latitude. To do that, we have to do 2 things. We have taken into account the fact that sun's radiation does not fall equally at all latitudes. All of you know that polar regions have 6-month long nights in which there is no sun's radiation, right, because the Earth is tilted on its axis. So, you expect polar regions to be cold, but if you want to calculate how cold it is, you need to do a more detailed analysis. That is one thing. Second thing is, if the temperature of the Earth varies with latitude from the equator to the poles, then you have to account for heat transfer from the equator to the poles. Okay. So, if there is a temperature gradient between equator and poles, heat will go along the temperature gradient. All of you know heat moves from high temperature to low temperature as required by the second law of thermodynamics. Okay. So, we have to extend the simple Lewis model which we use so far which was 0-dimensional model, we have to account for the sun's radiation varying with latitude and to account for heat transfer from equator to poles. For that, I have written a simple equation here, in which S by 4 is the radiation incident per unit earth area, and small s of I accounts for the variation of solar radiation with latitude, which comes from astronomy. Once you know the angle of the sun and the duration of the day and so on, you can calculate this quantity from astronomy. And 1 minus rho is the absorbed quantity. Rho is the reflected quantity, albedo is absorbed. So, left hand side is the amount of radiation absorbed in each latitude band, where phi is the latitude. Okay. On the right hand side, I made life easy by assuming that outgoing long wave radiation can be expressed as a simple linear function, okay, A plus bt. This is for the sake of simplicity. One can do a more complex model, but that will require numerical solution. We want to do it analytically. So, we make it a simple A plus bt, which is not a bad approximation, because you look at the OLR as measured by satellite from equator to poles, and the temperature as measured on the earth, one can show that the OLR measured by satellite and the temperature as measured on earth have a simple linear relationship. Okay. So, this is not a bad approximation for this purpose. And the last term is the energy transported from equator to pole. We assume that if the temperature given latitude is higher than the global mean temperature, it will lose heat to other latitudes, and those latitudes which are colder than the global mean, they will gain heat. Okay. This simple assumption that whichever latitude is warmer will lose heat to the colder latitude. Now, if you want to do the problem rigorously, you must represent this by a diffusion model, okay, like the way heat is transferred by conduction, okay, Fourier conduction law, all of you have heard about it. But that will make the problem more complicated, and again we will need a numerical solution. So, we will not do that, but you can look up textbooks and papers which do that. Okay. So, this simple model what we are going to use to look at temperature variation. Now, in this model you have to incorporate how solar radiation varies with latitude and season. Now, since we are going to talk about the annual mean temperature, we will average over all months. Okay. We will average all months and just give S as a function of latitude. Okay. So, if you take this particular result from astronomy, average over all latitude, you will get the following result, how the solar radiation varies with latitude. This has been made symmetric, is not exactly symmetric, because Earth's orbit around the sun is not a circle, it is an ellipse. So, there is a slight variation, we will ignore that for the simple model. So, we will make a symmetric representation of the incoming solar radiation annual mean, how it varies with latitude. Okay. Now, because incoming solar radiation varies with latitude, the absorbed solar flux is the highest at the equator and the lowest at the poles. Okay. Now, you see that this is not a smooth function. That is because the albedo of the earth varies with latitude. The albedo of the earth depends upon the kind of surface, land or ocean, forest or desert, and the amount of clouds. All these affect the absorbed solar flux. So, we have given here the actual measured value for your knowledge. There is actual measured value, and that the emitted long wave flux or infrared flux is also measured quantity from satellite, that is also given here. And this curve is shown to show that around 30 north and 30 south, okay, these two curves intersect. That means, between 30 south and 30 north, that is the tropics, we absorb more heat from the sun than we emit, while beyond 30 south, 30 north, the earth emits more radiation than it absorbs. Okay. So, this means that this shown here. So, energy gained in the tropics, energy lost in the mid latitude and polar regions, and therefore, there has to be some circulation which transfers heat from this region to this region. That is the one represented by this equation. This equation allows for heat to be transferred from the equator to the poles, because poles are losing heat more than they are gaining on an annual mean basis. So, you have to allow for heat to come, otherwise you will not have a steady state. Okay. So, this budget demands that heat be transferred from the tropics to the poles. Okay. Now, that curve I showed you of absorbed solar can be represented by the following equation, again simplified, where y is sine of the latitude. Okay. What do you find? That the solar radiation incident at the equator is 1.241 times the global mean, where radiation incident at the poles is 0.518 times the global mean. So, polar region receives less than half the radiation that is received in the equator. Okay. Now, we will assume that there is an ice line somewhere where the ice stops. So, above the ice line, y star is the latitude of the ice line. When y is above y star, we will assume that albedo of the ice and snow is around 0.62, and where the latitude is below the ice line, it is 0.32, typical of land regions. Okay. Now, this is only for convenience. These numbers are arbitrary. I have chosen for convenience. You can choose other numbers if you want. Notice that there are two values at y equals y star. Either it is 0.32 or 0.62. This is an abrupt jump. So, this is not realistic, but again for simplicity we have done that. With the above assumptions, you can write down the following equation for variation temperature with latitude. Okay. So, you take this equation, you put in the function of radiation variation latitude, assume albedo to vary in the way I have mentioned, and solve for T. These two are the two which will come on the one side, and others will go on the other side, the known quantities. And so, you get an equation where B plus D comes in the denominator for T of y. Okay. Now, remember that T m, the mean temperature is unknown, that is obtained from this equation, which all of you can see. For global mean, that is nothing but absorbed solar is equal to emitted radiation. Now, you have to know the Rome value, the albedo global mean, that depends on where the ice line is. Once you specify the ice line, you can integrate the albedo with latitude from equator to poles, allowing for change in area. Then you will get a value of rho m, and then from there you can get T m. And for example, if you put y star equals 0.5 as an example, where the ice line is at 30 degrees, then you will get T m of minus 6.32. You should put the numbers in check, you get the number. Then if you plot the temperature with latitude from that equation for two different ice lines 30 and 60, you will get a sharp jump at the ice line, which is purely an artifact of our assumption. Because we assume that the albedo varies suddenly at the ice line from 0.62 to 0.32. So, temperature also varies sharply at this point. If you had assumed a more smoother function of albedo, you would have got a much more smoother graph. Okay. So, this answer depends only on what you assume. This was done so that you can get a solution without using a computer, but you assume a smoother function of albedo with latitude, then you may have to do the problem numerically. But this problem shows how the assumption about albedo controls the sudden jump of the temperature at that latitude. Okay. So, this is a nice example which you can do at home with a simple calculator. You do not need a computer. For those of you interested, you can do a more complex problem and add a small program to solve for it, and then you will get a more smooth function of temperature with latitude. Okay. Now, this thing is shown from the lectures by Professor James Walsh in Oberlin College, where he has shown various examples. One, a completely ice free earth where ice line is at 90 degrees. Okay. You will get this value, or completely ice covered earth snowball where the entire temperature is between -30 to -50, or various other situations which we obtained in the last example. This is reproduced here. Ice line at 23.5, ice line at 45, ice line at 60.5. So, you can see that simple model can get you an ice free earth, ice covered earth, or ice line at various latitudes. So, I hope you see the elegance of the simple model. Although it is not very realistic, it reproduces the temperature variation with latitude for ice free earth, for ice covered earth, and for ice with ice line at various latitudes that you choose. And you got a good idea about whatever controls the location of the ice line. Okay. But of course, this is a very simple model. Such jumps do not occur in real world. In the real world, temperature varies smoothly with latitude, and that can be incorporated either by using an albedo, which is a smoother function of the temperature, or you can use a diffusion term in this equation. If you use a diffusion term instead of a simple model like this, the diffusion term is similar to what you learned in conduction heat transfer. That will be diffusion coefficient times d squared T by dy squared, where y is the sign of the latitude. If you put that term there, you can solve this problem analytically. You have to solve it by using a software, but that today is not too difficult. If you have access to good software, you can solve the problem. You will get a result which is somewhat different from this. You will get a more smoother answer. Okay. But I thought for this lecture, it is good for you to get a feel for this by doing it by hand, just using a calculator. Okay. So, that concludes my lecture on energy balance model, in which we allowed for change in latitude, temperature change in latitude. Thank you.